Yeah. So we're looking into solutions of the class test here, or class test that we wrote on the 27th of February. So let's look into question one. It was very straightforward and very short. Just a small class test, 17 marks. And we're supposed to be done in 25 minutes. It's counting down. So 1.1.1. So we need to determine the integral of each of the following. We have x squared multiplied by root x plus 3 dx. We need to determine the integral of the following. So ask the question within your group, what is integration or what is integration? So integration, someone said, yeah, they Google and say it is combining a complex and convex equation into one. So, but I said with you in your own understanding, what is integration? So when you see this side, we have this integral sign and dx. It means that we have a function which was derivated in terms of x. So here we need to try and find the original function that was derivated to get this function. So we have types of rules that we have. So I said when it comes to algebra, you have to think of, especially in product of function, you have to think of the chain of functions or the power bracket, like if I can give it in my own way. Or you need to think of uh, inverse trigonometric functions, the natural logarithms. So sometimes the functions we can have in disguise there, we can have at least the quotient of functions. But in product of functions, always you think of chains of functions. That's the first thing you need to think of. That you are trying to think in a way that if, let's say, I want to integrate the following function, I must have, let's say, an integral of, I must have a derivative and its function underneath the bracket of nth power. So that is the first rule we think of when we have product of functions. Product of functions. So please don't confuse it when you have just one function in a bracket or when you have just one function. That's the first one we think of. And again, we could think of integration by parts. But if we just have algebra, stick to the chains of function first. But if it doesn't work, we can go to by parts. Can go to by parts. I hope it's clear. I'm trying to emphasize that we don't just integrate, we check what functions are we having. If it's product of functions, what do we mean of product? You're having a function here and one inside the bracket. They are multiplying each other. After getting rid of the exponent, you still have to multiply with this f prime of x. So here it is a function underneath a rational exponent, which is half. It's to the power of half. I hope you see that. I hope you see that. Square root into exponential format, it is to the power of half. So now we're going to inspect first of all. We know that by all means, something outside the square root cannot be derivated and we get the square root. We know we cannot derivate x to the power of 2 and get this. But in disguise, we can try and derivate something inside the square root. We can get something outside there. That's why now in this case, when we need to use algebraic U substitution, we have to utilize and let what is inside the square root to be equals to U. So we're going to say let U equals to whatever is inside the square root, we're thinking that it can give us the derivative. So because we're seeing a bracket, we're seeing a function, the derivative of the function. So x plus 3. So I said to those who were here last week, I said you can utilize the whole square root, but you will always forget to substitute dx. So it's advisable that you utilize what is inside the root to be equals to U. From there, please don't forget to solve for x. When you see that this is a function and its derivative in disguise, because we see that when you derivate x, you cannot get x squared. So we need to even solve for x. That is the first thing. So solving for x, x is equals to take 3 to the other side. Take 3 to the other side. And x will be equals to u minus 3. U minus 3. And then from there, we can now derivate the function in terms of x. So derivative in terms of x, we know that derivative of the top one or of this bottom one, doesn't matter which one you derivate, still get the derivative. So we're going to have 1, isn't it? Equals to derivative of u in terms of x, we said is du over dx. Derivative of a constant, 0. So I said the other day, multiply the right hand side by dx, so we're getting rid of dx here. So that's why we see dx there. It's not that derivative of x is dx, we just multiply by dx. So we know that du is equals to dx if you have let something inside the root. But if you let the whole square root, therefore du is not going to be equals to dx. Hope it's clear the explanation that I'm trying to give. Then from there we know we have now x is equals to u minus 3 and dx is equals to du. So we can now substitute in our original function there, in our integrand. Therefore, we know that x is equals to u minus 3 and x was to the power of 2. And we are going to say that u is equals to this. U is equals to what is inside the root. So that's why you see I'm expressing the root in exponential form. And we have to replace dx. So we have to replace x, we replace the root there, x plus 3 by u, and we replace dx by, now we know it's equals to du. From there, now we can simplify further, because now it's taking us to power rule. When we utilize u substitution, we're going to use power rule by all means. We must have u as a function. We must not have x in the midst. At the moment you still have u and x, please note that it's an error. You haven't simplified until you have one function. So you must have one function, so therefore you can integrate. So in simplification, the square bracket here, I'm simplifying, I'm going to have u squared minus 6u plus 9, still multiplied by u to the power of half du. From there, we have to multiply out. Please don't lose the integral sign and du. It still means that we have to take back the function to where it was derivated from in terms of u now, in terms of u. When you multiply out, we have u. When you add the exponent, half plus that, it's 4. 5 over 2, isn't it? Therefore, minus u times 6u. 6u to the power of 3 over 2. Therefore, plus 9 times u to the power of half. We have to integrate in terms of u. I hope you see the notation, we're not losing it. It's communicative. From this step, now we can integrate from this step. Because we have an individual functions and the functions are in exponential form. And again, we have to integrate in terms of u. So utilizing power rule. So hence, therefore, our integral is going to be equals to, so we said you add 1. So it's going to be 7 over 2. And then 1 divided by 7 over 2 is 2 over 7. Therefore, minus u to the power of, we add 1, 5 over 2. And then 6 divided by 5 over 2. 6 divided by 5 over 2. 12 over 5. Therefore, plus u to the power of, we add 1 to exponent half, it's going to be 3 over 2. And then 9 divided by 3 over 2. It's 18 over 3. In fact, can we divide 18 by 3? It gives us what? Is it divisible? It's 6, right? Yeah. So we'll have 6. So, so therefore, plus the constant. Then we need to substitute back the functions that we integrate with. Okay, we replace in terms of u. Now we need to take back the function to be in terms of x. So we know that u is equals to x plus 3, all in all to the power of 7, minus 12 over 5 x plus 3, all in all to the power of 5 over 2. Therefore, we said this is 6. Therefore, u, which is x plus 3, yes, okay, allow me to write it at the bottom, plus 6 x plus 3, all in all to the power of 3 over 2, plus 6. So, if you want, you can express the solution there in root form. So, because we see that here we have square root of x plus 3 to the power of 7. So you can keep on changing into root form. But if you have it there, as long as you have replaced u in terms of x, now it's fine. I hope we see where we went wrong. Okay. So this is the basic rule that we have, we started with. So you're supposed to get your 3 marks just like that. So let's look into 1.1.2. So we had e to the power of negative 3 cot x multiplied by cosec squared x dx. So when you have the following, there's 2 methods that you can utilize, or let me say 3. But the first one is inspection method. When you utilize inspection, you say that by inspection, I want to try and look into because exponential function always changes exponentially. So this will appear when you derivate and when you integrate. So this came from a derivative, but we need to try and inspect the exponent. If we derivate the exponent, are we going to get a function that is multiplying the exponential function? Because this must be f of x, this must be f prime of x, according to exponential laws. Exponential laws state that when we need to integrate, we must have e to the power of f of x and its derivative. So we know that integral of that must be the exponential function as it is, therefore plus the constant. That is exponential law. So you can use inspection method and say, write down and say that, oh, when I look into the exponent, if I let negative cot x and say it's equals to f of x, therefore what will be f prime of x? So when you say f prime of x, I hope you see you will have negative cos x squared. But what is missing there? It's a negative and 3, isn't it? So negative 3 is missing. So which means when you integrate, we're going to divide by that constant, negative 3. So that is inspection method. But what if maybe some wanted to say that I want to let u equals to, negative cot x. Always when we let u equals to something, for an exponential function, we let the whole exponent, even if it was a square root, let the whole exponent to be equals to u. I hope that is clear. Always let the whole exponent to be equals to u. When you are trying to utilize u substitution, let u equals to the whole exponent. So therefore, in that case, when we have let u equals to the whole exponent, we can integrate. Okay, what is du? Du over dx is equals to derivative of this. It's going to be positive, right? Okay. Yeah, because derivative of cot is negative cosec squared. Multiplied by that is negative cosec squared. So it becomes positive cosec squared. I hope you see that. So at least, okay, I wanted to say let's multiply by dx on the other side because we're utilizing is du over dx multiplied by dx on both sides. So in that case, now we're going to even replace dx there. The meantime, let me substitute dx. So dx is equals to du all divided by 3 over cosec squared x. So we divided on both sides by cosec squared. So in our original function, let us replace. So we said negative 3 cot x is equals to u. Therefore, we have our cosec squared, which we haven't replaced in terms of x. But dx, we said, is equals to du all divided by 3 cosec squared x. So in that case, I hope you see when we utilize u method, something must be divided always, or we must replace in terms of x. So we've divided cosec squared by cosec squared, therefore equals to, we have e to the power of u, therefore du. So I have to integrate the exponential function in terms of u. So it's like e to the power of x in terms of dx. So therefore, we know that it's going to be e to the power of u. We're supposed to divide by the derivative of the exponent in terms of u, which is 1, and ln e, which is 1. So thank you for that. 1 over 3. Please factor out 1 and factor out 3 there. So we have 1 over 3. So I'm focusing on the function. So therefore, in that case, we'll have 1 over 3. Therefore, e to the power of plus c there. So the exponent is negative 3 cot x when you substitute back. So it's 1 over u, 1 over 3 eu plus c. You replace back the functions, therefore we have our function 1.3. So we're supposed to have, we're having 1 to say over root 9 minus 16x squared dx. So it was 1 over 9 1 over root 9 negative 16x squared plus dx times dx. So please try and utilize your formula sheet. In most cases, your formula sheet must be your friend. Your formula sheet must be your friend. Even now, it must be your friend. Because when I ask something, you must have an idea, but at the end, confirm using your formula sheet. Okay, let's inspect the functions now. The first thing we see in the numerator, we have a constant. In the denominator, the function is inside the square root. Or we have a function inside the square root. So please, the moment you see you have one function in the denominator, try and think of inverse trigonometric functions. Always think of trigonometric functions. If you see square roots, and you have functions inside the square root. But if let's say you just had a function is all dividing, let's say a constant, try and utilize your partial fractions or by parts, not by parts, this long division, but seeing a square root, think of inverse trigonometric functions and trigonometric substitutions. Trigonometric substitutions. You can utilize that. As long as you just have a function subtracting a constant or it's added, a function it's being subtracted by a constant. So please don't think of ln of the denominator or thinking of u substitution. It won't work because here the function is only one inside the bracket. I'm repeating many times because you think of u substitution and it's not u substitution. U substitution is when you have product of functions. Here we just have one function only inside the square. So in that case, when you see a constant, maybe a term with a function subtracting and it's all squared, try and you think of arcsine or arccos. With arcsine, we know that at least it must be a positive constant. With an arccos, you were supposed to have a negative there. So which means we need to try and simplify this problem. One thing, you must try and express this as a squared and this as bx squared. Or if you want, utilize it and make sure you have 1 squared, and here you must have a function f of x to the power of 2. That's how you do it. How will you do that? So if you want to just have 1 squared, please take out a common factor of 9. If I take out a common factor of 9, divided 9 by 9, I have 1. If I divided 16x squared by 9, we're going to have what? 16x squared, all divided by 9. So that when I still multiply, I'm still going to get the top expression underneath the root. Simplifying further, please recall what we call laws of sets. If you have factors multiplying each other, 9 is multiplying the bracket, you can split the root of 9 and root of 1 minus 16x squared over 9. I hope you see that. Set rules, been talking about that. So still have 1 over. So root 9, we know that is 3. Therefore, inside we are left with 1 minus 16 x squared over 9. Please try and express it in perfect squares. Perfect squares, we mean that express it in as a square. How can I express 16 as a square? I can have what? 4 squared, isn't it? And x can be x to the power of 2. And then 9, expressing it as a perfect square is going to be 3. Then as a perfect square to the power of 3. 2 to say. So we just factored out 1 exponent. So expressing it as a perfect square, it's 4 squared, 16 x squared, and 9 squared, which is still 9, or 3, which is 9. Now, according to the formula sheet, it states that, in fact, let me put it down. So, derivative of arcsec, I'm just doing this. It was supposed to be what? F prime of x, isn't it? All divided by what? Root of 1 minus plus 1 minus f of x all squared when you derive something like that. So we're trying to express it in that format, Yeah, explaining along. Okay, so I want you to look into that formula sheet. In your formula sheet, does it not say the arcsine 1? So what does it say there? So I wanted you to see that, we're having 1 minus f of x all squared. So a formula sheet states that if we have expressed it in that format, I hope you see there we have 1 over 3 still multiplying the function that we have to integrate. It's a constant, 1 over 3. Even your textbook have your formula sheet. So make it your friend. You must make sure your functions, you relate them to. So look at your formula sheet. So I want you to give me an answer. At least I've tried to express it for you in a function and squares. Formula should have expressed it as 1 squared, so that it must be easier for you, because you might make a mistake when you couldn't express this as a square and that as a square. So our x, which is 4 over x over 3, we're supposed to divide by what? By a, which is 1. So that's the function. So therefore plus what? Plus the constant, plus c. Plus c. Okay, I hope it is clear. I hope it's clear, just like that. So always you are there when you see integral of roots, just think into that. If you want, you can express this as a perfect square and that as a perfect square. So that when you go there, you'll say arcsine a over x over b. It's not just x, the function which is squared there. You still get the answer. So if you want to make it look like a formula sheet, express this as a perfect square and this as a perfect square, which is 4x all in all to the power of 2 dx. So this is very important. Even the coefficient of x must be expressed as a perfect square because it was derivated from somewhere to have the 16 there. So that if you utilize that formula sheet, you can say in integral, which is going to be equals to arcsine. It will be arcsine. And therefore here we're supposed to have. So your formula sheet says what? I'm trying to recall the formula sheet. So it's x over a plus c plus c. I think the formula sheet might have forgotten the constant because it must be 1 over a. Must be 1 over a arcsine is x. I'm just trying to recall that. So it's 1 over a. As I know the inverse trigonometric functions, it will be that. It will be this the f of x, and therefore I will say arcsine the f of x. So the constant, just here I had the constant, I will be multiplying by that constant one. So please recall inverse trigonometric functions. I recall that. It's because of time I wanted to go to trig substitutions. Trig substitutions. So if you see this minus that, you let what is inside the square there to be equals to psi. You let it equals to psi. Okay. I want us to look into 1.1.4, where we had cos 8x multiplied by arcsine, not arcsine, by sine 5x dx. Sine dx. Okay, before we even solve the problem here, so it's just that from the head, I've forgotten the rules. You need to recall different, what do you call, coefficients of the angles, different of what is it, of cosine and sine of the angles there. So the coefficients are different, the angles. So we say these are difference of the coefficients of the cosine and sine functions. So remember, when we see product of two functions, we always said we must have what? A function and its derivative. But when we inspect here, when we derivate sine 5x, we cannot get cosine 8x. That's not true. We're supposed to get cosine 5x, isn't it? So make sure, remember, when you derivate a trigonometric function, you must get the same angle. A sine function with the same angle. So we inspect derivative of 8x cannot give us sine 5x. It was supposed to be sine 8x. So which means here this is a different coefficients of the angles. We have to utilize the identities. So in the textbook, I just want us to write them down before we even utilize them. Because here we don't have the derivative, we don't have the function. Even if you wanted to use double angle identities, still again, we cannot have a function and the derivative. So we need to utilize the function. If let's say we have cos, let me say ax sine bx. The solution for that must be half. If we started with cosine, it must be half sine what? So if we started with cosine and then multiply by sine, it must be sine. Therefore, a plus, or let me utilize the angle too. So let me utilize the angle, but though I didn't want to use the angles. Okay, let me remove the axis. Let me remove the axis. So to make sure that you see that cos A sine B equals to half. The proper identity will be sine. Therefore, it will be A plus B. In the second term, I think it must be minus, right? Yes. So minus sine, or it's plus sine A minus B, close bracket. So this is an identity. We're not in the integral. And I just want to write all three of them, but I think it's four. So if let's say we start with cosine A, must be cos and cos of different angles. So it's cos A plus B plus cos A minus B. Okay. All right, so the one for sine. So if let's say we have sine and sine of different angles, it must be half into. So it's cos A minus B minus cos A plus B. So if it's a cos and sine of different angles started with sine, therefore it is minus in between, then minus there, then for sine and sine. Then what if let's say we had sine A and then cosine B? I hope you see now. So it is now we start with sine, then follow the cosine of a different angle. So it must be sine A plus B plus sine A minus B. Close shop. So this is the one that I know from the head. The rest I always have to recall. So sine A cos B must be sine A plus B plus sine A minus B. So those are the identities you need to recall of different coefficients of angles. Different coefficient of angles, of sine and cosine, or sine and sine. So when we try and inspect the one on top there, the one that is given to us. So we need to utilize the first one, isn't it here? So we are going to say now our integral. So please pay attention. Don't lose the integral sign. So I know when you utilize the identity, you can write maybe on top and say that if I have cos A sine 5x, it will be half 1, 2, 3. But come back and substitute back to the integral and say that it will be half in bracket sine. I hope you see. So it will be A plus B, isn't it? So our A, 8x plus 5x, which is 13x, isn't it? Therefore, we'll have minus sine. It will be 8 minus 5x. So 8 minus 5x will have 3x. Close shop. And multiply by what? dx. Don't forget that. Because we're integrating. So let's not forget that even though we're utilizing the identity, we still have to integrate the function. So we're trying to simplify into its simplest form. That now at least we have sum or difference of functions. So we can integrate them. So in this case, before we integrate, let me do this. Half still multiplies sine there. That's why I want to say sine 13x. We can integrate it in terms of x. Therefore, minus half still multiplies, and then we'll have integral of sine 3x dx. So I want to show you that at least we have individual functions. We are not having product of functions. That identity helps us to have the difference of functions. So therefore, we can now integrate. Half still multiplies now the integral of that, but integral of sine, it must be what? Remember, what did we derivate to get sine? We derivated cos, isn't it? So there's a missing negative sign. Pay attention to that. Because derivative of cos was supposed to be negative sign. I hope it's clear, so we don't have negative sign. What do? We need to divide by that negative sign. It's cos now 13 x. Divide by the negative sign and what? The derivative of the angle, which is 13. So here you can do it in two ways. We have the negative sign already. You can just embed it and say positive cos. Or if you feel like you make a mistake, just look into saying that integral of sine must be negative cos. It must be negative cos 3x all divided by that negative 3 plus c plus the constant. The rest that we're left with is to simplify. We're left to simplify. Okay, I can write it just there on top. That in simplification, we will have a negative cos 13. Yeah, so negative half times 1 over 13. So half times negative 1 over 13. 1 over 13 times 1 over 2. It's negative 26. So I have to look into 1.1.5. It's given as, we need to put integral sign there. It was missing, a mistake. Cos to the power of 5x multiplied by sine to the power of 3. So this is the powers of sine and cosine. So trigonometric powers. We have to integrate. So to sum, I said if both exponents are odd, please you can change any of the functions to the power of 1. At least I have to the power of 1. But normally take the one which is to the having a lower, let's say, value of the power, like this one. So it is a smaller exponent, which is 3. So we can utilize that one. But even if you can utilize this, it's still fine. You still get to the same answer or same gradient. You still get the same equation. When you derivate, you still get the same gradient. So let us utilize the powers of trigonometry. This one, even if let's say you wanted to say, when I derivate cosine, do I get sine? Yes, we can get sine, but not sine to the power of 3. But if you derivate sine, can we get cos to the power of 5? No. We can get only sine, cos to say. At least the coefficients are the same. Inspect the coefficients, inspect the powers. So we have product of two functions. So hence that's where we can drop down the exponent using the exponential laws. We are going to express this one as power. We'll have sine x times sine to the power of 2, isn't it? Dx. So I have sine the power of 2 times sine to the power of x. We still get sine cubed. The second step after utilizing exponential laws or splitting the same basis, different powers. Now we go to utilize the trigonometric identities. Because at least we're trying to have that law of saying I have a derivative and a function. A derivative and a function. So at least we know when we derivate cos, we can get sine. So at least this can be our derivative. We need to make this our function. But we need to resolve that at least to combine and have one function with this one. So we know to get it to cos, we need to use square identities. So we'll have cos to the power of 5 multiplied by sine x. Therefore, what is sine squared in identities? 1 minus cos squared x dx. That is the first step. So at least now you can even utilize U method and say, this is my function, this is my derivative. And let U equals to cos x. Let U equals to cos x. Okay, so but utilizing the multiplication state is cos x sine x times 1. Cos x to the power of 5 sine x times 1. We have cos to the power of 5 times sine x times 1. Multiplying the second term, cos to the power of 5 times cos to the power of 2. It's cos to the power of 7, isn't it? We add the exponents if the bases are the same, times the sine x. Therefore, dx integrate in terms of x to sec. So we have multiplied out the bracket there by cos to the power of 5 sine x. So we have that. So I hope you see now, not in disguise, but straight away we have a function and its derivative. So I have cos. Should I do this for n5s? We have cos to the power of 5. For n5s, I'm not supposed to do this. To the power of 5 times sine x. So this is what we say multiply. This is the function, this is the derivative. So cos is underneath the bracket to the power of 5. So we know when we derivate cos, we must get negative sine x, isn't it? So you'll know that, oh, something which is missing, it is the negative sign, isn't it? So you'll have to divide by that negative sign. So derivative of cos was supposed to be negative sine x. We're just missing the negative sign. So we know this is our derivative in sine. So we can add 1 and divide by that exponent. So inspect it in that way. So I know that integral of that, I have a derivative there, so it will be cos to the power of 6. I must divide by negative 6 because we said there's a missing negative sign. We're supposed to have negative sine x. So same thing to the second term, at least the negative is there. So even if we don't divide by the negative, so we're just going to say positive. We're going to say cos to the power of 8, all divided by 8, plus the constant. So note that I didn't divide by negative 8. because already I've taken it to positive. We know that, oh, there's a negative sign x. So I just add 1 and divide by the exponent. Just like that. So the derivative of cos x is supposed to be negative sine x. At least we have the negative there. So we just add 1 and divide by the exponent. I hope it's clear. But if you want, please put the negative here and divide by that negative. At the end, it will be negative and positive. Be negative and positive. So that's what we're supposed to have. Trigonometric powers. For this, we did it the day before the test. Oh, that was the last one. I was like, let's carry on.